Welcome students for the second chapter spectroscopy. Here you have studied up till now in the first chapter elementary quantum mechanics. You have studied introductory part, the difference between classical theory and quantum mechanics, then de Broglie equation, hypothesis, Heisenberg uncertainty principle, black body radiation, then Planck's quantum theory, Compton effect, then Schrödinger wave equation, derivation of Schrödinger wave equation, then particle in a one-dimensional box, and also you have derived the energy of a particle at a zero level, that is the when principal quantum number n it is equal to 1. For that we call that energy is 0 point energy. Again you have studied the quantum numbers, and there are 4 quantum numbers: principal quantum number, azimuthal quantum number or angular quantum number, magnetic quantum number, and spin quantum number that you have studied. And if you have any difficulty in the understanding of the first chapter elementary quantum mechanics, you can ask me and get that chapter properly studied. Your study, it is an important one. So let us begin with the second chapter, and the name of the chapter it is spectroscopy. Already I have given you the subpoints in the second chapter. Still I will revise all that points once again. In the second chapter you have to study the introductory part, then electromagnetic radiation, electromagnetic spectra, then rotational spectra of diatomic molecule, vibrational spectra of diatomic molecule, Raman spectra of diatomic molecule, and comparative study of the IR and Raman spectra, rule of mutual exclusion for CO2 molecule, and the problems based on this chapter. These are the subpoints that you are going to study in this chapter. Here, all of you know spectroscopy, it is the branch of science and which deals with the study of interaction of electromagnetic radiations with matter. In short, the spectroscopy, it is the study of interaction of electromagnetic radiation with matter. And what happens when any matter it absorbs the electromagnetic radiation? Here the uh, you know molecules, they are made up of atoms, and atoms they are made up of electrons, and at the center there is a nucleus. Then by the absorption of energy, the electrons in the atoms they get migrated or they get transferred from lower energy level to the higher energy level, and this phenomenon it is called as transition of the electron from lower energy level to the higher energy level, and this occurs because of the energy or photons energy is absorbed by that electron, and at that time we obtain the absorption spectra. That means absorption spectra, it is the interaction of electromagnetic radiation by the matter. Then in the emission spectra, the electrons from the higher energy level, they return back to the lower energy level, and at that time we obtain the emission spectra. Again, the nature of atomic spectra, it is very simple one, and the nature of the molecular spectra, it is complicated one. Then the molecular spectra, it is also called as the band spectra. Here atomic spectra, it is a only we have lines, and in the molecular spectra we have large number of lines pasted together. That is the molecular spectra. Here again, for the next lecture you have learned the electromagnetic radiation. The term electromagnetic radiation represents the radiant energy emitted from any source in the form of light, heat, etc. Some important characteristics of these electromagnetic radiations are given below. They have dual character, that is particle character as well as wave character. For example, a beam of light is a stream of particles called photons moving through the space in the form of waves. Then the next characteristic, these waves are associated with electric and magnetic fields oscillating perpendicular to each other and also perpendicular to the direction of propagation. And the next characteristic, all electromagnetic radiations travel with the speed of velocity of light. Then the regions of electromagnetic radiations with particular wavelength, particular frequency and the source. As already I have told you, the arrangement of these waves or wavelengths here, cosmic rays, they have wavelength from 0 to 0.001 angstrom unit, and they have the frequency, it is in the order of infinity to 3 into 10 raised to 21, and they are present in the outer space. Here gamma rays, they have wavelength 0.001 to zero point 0.1 angstrom unit, and their frequency, it is the 3 into 10 raised to 22 to 3 into 10 raised to 19, and gamma rays we have in the radioactive substances. Then X-rays, here their wavelength range in between 0.001 to 100, and the frequency lies in between 3 into 10 raised to 20 to 3 into 10 raised to 12. And we have X-rays we generate X-rays by the bombardment of certain metal with cathode rays. Here, the next electromagnetic radiation called as ultraviolet rays, and their frequency, it lies in between 1 to 3800 angstrom units, and the frequency, it lies in between 3 into 10 raised to 12 to 7.9 into 10 raised to 14. And the source of ultraviolet rays, it is the hydrogen or deuterium discharge tube or a component of sun's rays. Then the visible light, visible range. Here these wavelengths are in angstrom unit, remember well. Here the range of visible waves, it lies in between 3800 to 7600. That means 380 nanometer to 760 nanometer. And the frequency range, it is 7.9 into 10 raised to 14 to 4 into 10 raised to 14. And the source of visible range, it is the sun or any incandescent solid. Then IR, that is infrared rays. Their wavelength 7600 to 3 into 10 raised to 7, and frequency, it is 4 into 10 raised to 14 to 1 into 10 raised to 11. And the source of IR, here it is, we get IR by vibration of molecules, for example by heating rods of special materials. Then the microwaves, they have wavelength 3 into 10 raised to 8 to 3 into 10 raised to 11, and their frequency, it is 1 into 10 raised to 10 to 1 into 10 raised to 7. And we get microwaves by oscillations of electrons in a wire, that is from alternating electric current. Then radio waves or TV waves, here the wavelength lies between 3 into 10 raised to 7 to 3 into 10 raised to 14, and their frequency is 1 into 10 raised to 11 to 1 into 10 raised to 4. And as we get the microwaves by oscillations of electrons in a wire, that is from alternating electric current, we get the radio waves. Then the molecular energy level diagram. Remember that each molecular energy level diagram, it consists of electronic energy levels, vibrational energy levels, and rotational energy levels. And the energy required for the electrons for electronic transition, it is greater. And here in this diagram, they have shown there are two electronic energy levels. This is the first one and this is the second one. Remember, the energy required for the electronic transition, it is greater one, and the electronic energy levels, they are shown by the n value. That means here n it is equal to 1, here n it is equal to 2. Then the each electronic energy level, it consists of vibrational sub levels, and the vibrational quantum number, it is written by phi, and they have the values phi equal to 0, 1, 2, 3, 4. This is the first energy level of electronic. It consists of sub-vibrational levels, and for second electronic energy level there are again vibrational energy levels as 0, 1, 2, 3, 4 and so on. That means electronic energy levels, they are associated with sub-vibrational levels. Okay, and then the energy required for vibrational energy transition, it is quite less as compared to electronic energy level. And the each vibrational energy level, it is associated with the rotational sublevels, and rotational sublevels, they are denoted by the quantum number J. Here this vibrational energy level from 1 to 0 to 1, 1 to 2, 2 to 3, they are associated with the rotational energy levels, and rotational energy levels shown here, they are 0, 1, 2, 3, 4, etc. Then the next energy level of vibrational, here the rotational energy levels are 0, 1, 2, 3, 4, etc. Remember, the molecular energy levels, it consists of electronic energy levels, vibrational sub-energy levels and rotational sub-energy levels. Rotational sub-energy levels, they are denoted by J values. Vibrational sub-energy levels denoted by phi values, and electronic energy levels denoted by N values. And the energy required for electronic transition, it is greater than vibrational energy level transition. It has less energy required, and again less energy is required for the rotational transition. That means here you can see the rotational transition from 0 level to 1 level. It requires very less energy, and from 1 to 2, 2 to 3, 3 to 4, these are the rotational transitions. Simply remember here the molecular energy level, it consists of electronic energy levels, vibrational energy levels and rotational energy levels. The energy required for rotational transition, it is very less. Then energy required for vibrational transition, it is greater, and again the energy required for electronic transition, it is again greater. Here absorption and emission spectra. As you know, due to absorption of quantum, the electrons at lower energy level, they jumps from lower energy level to higher energy level, and at that time we obtain the absorption spectra. And here the E2 energy, it is greater than E1 energy. This is the reason for getting the absorption spectra. And in this diagram, in the B diagram, we have shown the emission of emission spectra. Here the molecules, they return back to the ground level or low energy level. At that time we obtain emission spectra. Here A diagram, it is shown, it shows the transition involving absorption of photon, and the B diagram, it shows the transition involving emission of photon. Then, according to Born-Oppenheimer approximation, the total energy of a molecule is the sum of translational energy, rotational energy, vibrational energy, and electronic energy. And in the form of equation, we can write the total energy of the molecule. It is equal to energy required for translational motion of molecule plus energy required for rotations of molecule plus energy required for vibrations of molecule plus energy required for electronic energies. And it is found that the translational energy is very less. So it is negligibly small, and hence according to Born-Oppenheimer approximation, we can write as the energy of molecule, it is the sum of rotational energy plus vibrational energy plus electronic energy. And as I have explained to you in uh, the molecular energy level diagram, that the energy required for rotational transition, it is less than energy required for vibrational transition, it is greater than rotational energy, and the energy required for electronic transition, it is greater than vibrational energy level. The total energy of the molecule, it is the sum of rotational energies of molecule, vibrational energies of molecule, and electronic energies of molecule. Then the types of molecular spectra. In this chapter, here you will understand what is the pure rotational spectra. And rotational spectra, it is also called as microwave spectroscopy. Then the vibrational rotational spectra, then electronic band spectra, Raman spectra, nuclear magnetic resonance, it is not included in our syllabus for the physical chemistry. Again, electronic spin resonance, it is also not included in our spectroscopy chapter. But these are the molecular spectra. Then this diagram, it shows the regions of the electromagnetic spectrum. Here already you have studied this. Then our first point, here it is pure rotational spectra of a diatomic molecule. Here suppose this is a diatomic molecule. This M1 atom, it is our hydrogen atom, suppose, and M2 atom, it is our Cl atom. HCl molecule, it is a diatomic molecule, and this one is the bond length. Okay, and here the rotations of this diatomic molecule, that takes place at the center of gravity. The center of gravity does not change, and rotations takes place end over end rotation. Then this bond length, it is a rigid one. Such a model, it is called as rigid rotator. Rigid rotator means that molecule, it has a rotations at the axis, at its axis, and end over end rotations takes place. Here suppose the distance of M1 atom from the center of gravity, suppose R1, and the distance of M2 molecule from the center of gravity, suppose R2, and the total bond length, here it is R. Then according to the quantum mechanics, the energy of rotations, it is given by the equation h square upon 8 pi square into I, where I, it is a moment of inertia, and here J into J plus 1. This is the J quantum number, and this is again quantum number J. And moment of inertia, this is equal to reduced mass, here m1 m2 upon m1 plus m2 into r0, and it is denoted by nu into r0 square. Here this equation is for the moment of inertia I, it is equal to mu into r0 square, where r, it is r0, it is the bond length, and mu, it is the reduced mass. Here m1 and m2 are the atomic masses of the two atoms of diatomic molecule. Here it is called as reduced mass, the product of two masses divided by sum of two masses. This ratio, it gives the reduced mass. Again, here this is the I, it is equal to U into R square, and it is equal to L. That means angular momentum, it is given by I into omega. Therefore, the angular velocity or angular momentum of a moving body, it is given by square root of j in a bracket j plus 1 into h upon 2 pi, where j, it is equal to 0, 1, 2, 3, etc. And these are called as rotational quantum number. Then according to classical mechanics, the energy of rotational molecule, it is given by I into omega square, where omega, it is the angular velocity. Remember that as per the classical mechanics, energy of rotational molecule, it is given by I into omega square, where omega, it is the angular velocity, and it is equal to 1 half I omega square. That means I into omega square upon 2I, it is equal to L square upon 2I. If we take square of this L, then we can get in rotational energy, it is equal to J in a bracket J plus 1 into h square upon 4 pi square into 1 by 2I. That is ER, it is equal to h square upon 4 pi square into I into j in bracket j plus 1. And by putting here the values of j equal to 0, j equal to 1, j equal to 2, and so on, we will get the rotational energies for particular j values. Here, when j equal to 1, we get this value as 0. When j equal to 1, we get this value. When j equal to 2, we get this value. J equal to 3, we get this value. These are the rotational energy level diagram of a diatomic molecule. And in this diagram, you will observe that as J values increases, the spacing between the energy levels, it goes on increasing. This is the rotational energy level diagram. Then the rotational selection rule here, delta J, it is equal to either plus or minus 1. The transition for J equal to plus 1 corresponds to absorption spectra, and J equal to minus 1 corresponds to emission. This is the energy of rotational energy. It is given by h square upon 8 pi square I into J in bracket J plus 1. Here, for one quantum energy, it is given by E, it is equal to h nu. This nu, it is a frequency, and h, it is a Planck's Planck constant. H, it is a Planck's constant here. Therefore, the energy in terms of frequency we can write as, by this equation, nu it is equal to E by h. Therefore, the rotational energy in the frequency we can write h square upon 8 pi square into I into j in a bracket j plus 1, and this is the, we replace this by j, b into j in the bracket j plus 1. Therefore, rotational energy in terms of frequency we can write h square upon 8 pi square I into j in bracket j plus 1. Here we have replaced the h square upon 8 pi square I by letter b. This b, it is a rotational constant. Therefore, this is the simple equation. That means the rotational energy in terms of frequency we can write b j in a bracket j plus 1, and the delta ER, it is equal to the transition from higher energy level to lower energy level.
Doctor, in Python, they are perhaps use a similar framework because
This is again,
there is some concept of indentation
here
where
I have calculated the delta
if you take
ER value,
or to write each statement, there has to be
and
four,
it is
four
given by
spaces has
2b
to be kept there.
in bracket j plus 1. Here in this diagram, this is the first transition from 0 to 1 value. Here, second transition from 1 to 2, third transition from 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, here 7 to 8, here 8 to 9, and 9 to 10. These are the J values, that means rotational constant values, and by putting these values we can have the rotational energies in terms of frequency. Here for j equal to 0, 0 energy, j equal to 1, 2b energy, Here 6B energy, 12B, 20, 30, 42, 56 and so on. And similarly here we can obtain, these are the lines for particular transition. This is the first line for transition of from 0 to 1, j equal to 0 to 1. This line we get for the second transition from 1 to 2 level. This is the third line for transition 2 to 3. This is the next transition from 3 to 4 J value and so on. And this is the pure rotational spectra, nature of pure rotational spectra, and the distance between these two lines, it is always constant distance, and that distance is 2b. Okay, thank you. We will see next time the relative intensities of rotational spectra. Okay.